I will try to give you an insight of what is really the situation, because every week, probably hear something or you see some videos on YouTube. So, but first I want to introduce you Rimac or Rimac, and this is it. It's the world's fastest electric vehicle, the hypercar. So just at a glance, some performance. The top speed, 355 km/h, 1.2 mega horsepower, and acceleration 2.5 to 100, and 14 seconds up to 300 kilometers. And Rimac, okay, are selling cars, but not only. They are developing the technology. These cars are also the showcase. So autonomous driving, for example, it's one technology that is developed. And some example of work we did for the Koenigsegg, we did the world's most power-dense battery pack. For Aston Martin and Red Bull are working on developing a road car that is incredible, that it's the ultimate hypercar. And for that also, we have a know-how to do, and we develop the battery system. And the last example here, it's in 4 months, our team designed, developed, set up, and tested this 1.1 megawatt race car for one of the most prestigious race in Pie Peaks in the United States. So, with me here are my colleagues from GRAPE. GRAPE is a part of Rimac, and GRAPE is the brainchild of the people who worked on the Concept 1. The idea was to apply the technologies developed for hypercars to some other type of applications. And for example, here you see the second generation of this electric bike, the G12. You can see the performance. I will not pass through. And I invite you to visit them in our booth close to the main hall. And the last pictures is basically, we are fans of football, so this is a personalized car for Fabregas, Messi, and Piqué. Not cars, but bikes. So let's go now. So what about autonomous driving? There's a lot of talk. So it started a long time ago in books, in science fiction, but concretely, let's look at some statistics. Every year, 1.2 million people died in a traffic accident worldwide. And 90% of the cases of crashes are human error. So there's a lot of reason. There's alcohol, of course, in case. For 63% of deaths are due to alcohol. And 14% of car crashes are due to use of cell phones. So distraction is an important matter. So there's people working on this autonomous driving, us trying to solve all these issues. And Google, you know probably, with this Google car, that's not beautiful, but it's not their goal. Their goal is to provide a good technology as a taxi. And you see they have a kind of sensor on the top of the car. You cannot imagine this type of sensor on our car, Concept 1. Yeah. And on the other side, you see the picture of ring speed exchange concept. What would be in the future the autonomous driving? So you can relax and take the travel. But it's not enough, because you can sense what is around the vehicle, but how to sense more far and know what happened in the traffic? So that's why the idea is to connect vehicles. And this is the map you have here below. The car will communicate between them. They will communicate with infrastructure also. And the goal is to achieve someday 0 fatalities. But when? That's very important to understand. Today's goal is to reduce the number of accidents by 90%. When? 2040. 2040. Okay? So, also, you saw this connected block. So you can imagine that when you enter in the city, you are like coming in a mothership. And the city will take the control of the car and leads you to optimize the traffic. And so it will reduce the traffic jam, it will reduce the consumption. And also for old people who cannot drive anymore, it enables mobility. So about development plans. Well, I said 2040, we want to achieve 90%. So what you have on this curve, you have, it's a forecast by McKinsey. And the blue curve you have here shows the high disruptive scenario for full level 5. It's a full automatic driving, no more driver involved. And in 2030, the goal is that we have 15% of market share. This means 14 million vehicles. And if it's not the case, if there's no user acceptance, it will take much more time. And so here I just summarized some challenges. One big is technical, yes, still, even if some are saying no. How to test if a vehicle is safe is also a challenge. The cybersecurity, you can imagine. You are experts probably in this, and the user acceptance. So let's look briefly at a simplified architecture. You need sensors. So you need something that will help you to localize where you are. It's a kind of GPS and inertial measurement unit. But you have to be aware that using a GPS is not very precise. It's 10 meters. Within 10 meters is enough to have a crash. So you need to add on top of that some algorithm that will build you something that is can localize yourself within a few centimeters. You have cameras, because with cameras you can detect objects and recognize them. With a radar that you have also, you can detect objects, but you cannot recognize them. And with a LiDAR, which is, let's say, basically the same as the radar, but it's a laser, you can also recognize objects. And one important thing to have is connectivity is the vehicle to X, vehicle to vehicle, vehicle to infrastructure. And you need a car that is drive-by-wire. You need to control all the organs. It means the steering, the brakes, the gearbox, the motor. This is very important. And what are the 4 algorithmic blocks? Environment understanding, we will go through very briefly. Localizing and mapping. So this is also something that can be strange, because you need to find yourself, to put yourself in a map, without having a map in some way. And to build a map, usually, you need to know where you are. So this is also a kind of paradigm. You need to plan the motion, meaning that how do you go there? Is it safe? The path, is it safe? And we are in a time-changing environment. Always something new happen. And the driver monitoring. If you are not fully automated vehicle, then you always need to give back the control to the driver. And you need to know if he's not sleeping or doing something else. If you have a dangerous event, can you give it back, the control, if he's sleeping or reading a book? So that's basically what I passed through that. But you need also to build a fault-tolerant system. There's no perfect sensors. Things happen. Shit happens. So a sensor can fail. And if you're in autonomous mode, yeah, it should not lead to a fatality. So you need to have redundancy, like in a plane, for example. But also in terms of software that you are very familiar, you need to have a fail-safe software, meaning that you should never stay too long in some loops. You should never crash in some way. So that's, as far as I know, there's no procedure that can help to build a fail-safe software. Usually there's a lot of tools that helps, okay, but there's still a lot of testing that is needed. And where we put the intelligence? That's a question. In fact, we can put it everywhere, but is it clever? That's a good question. For the environment understanding, yes, for sure. For the localization mapping, we can, but should we? That's another point. I will not enter because lack of time. In the motion planning, usually it's probabilistic approaches. Can we go? Is the space empty or not? Well, we can add also some machine learning on that. And driver monitoring, it's a place where we have for sure machine learning because, for example, you need to extract the heartbeat, you need to check the gaze of the eyes, if the driver is watching the road or not, what he's doing, if he's not sleeping, drowsy, or whatever. So, I just want to give you one example, a little more in detail. It's the problem of perception. So, the goal is to understand the surrounding. For that, you need to detect. Detect means just know if there's an object that is not what you consider the background. It means from the list of objects that you want to detect, is something from this list existing? Then you need to recognize, what is it? Is it a car? Is it a pedestrian? Is it a bicycle? Is it a car, a cat or dog crossing the street? A traffic sign? So you need to segment it. I mean, cut, let's say if it's an image, cut the image around this object to know exactly where it is, to be able to find the distance and the size. And for all of these objects surrounding the vehicle, you need to assess the danger. This is difficult, because imagine you have a cotton box on a road, and you have a metallic box. The cotton box you can pass through with your car, nothing will happen. But the metallic box, you will break your car. So how you will distinguish this? Assess what is dangerous. If you have a pedestrian on a trottoir, will he cross the street or not? So this is events you need to predict. And in perception, you have three problems. One is misclassification. It means I mistook what I detected. I detected the dog, it was a pedestrian. What's the impact on my system? Then you have false alarm. What is a false alarm? Look, I am driving on a highway, 130 kilometers per hour, and suddenly my sensors detect, or my intelligent machine learning detects that there's a car or pedestrian just appears in front of me. And it brakes, but there's no pedestrian. There's nothing. So you can be involved in an accident just by this type of mistakes. And the miss rate, which is obvious, is I didn't detect the car, I didn't detect the pedestrian. So don't think that this is a solved problem. You cannot achieve 100% accuracy. It's a utopia, because it would mean that you have an infinite amount of data, which you can never collect. So, for example, the classical way of machine learning to detect a pedestrian, you see, for example, you have some errors. The bench here is detected as a pedestrian. This is misclassification, typical example. So, after, for example, if you use a different type of approach, for example, everybody, I think, heard about deep learning and deep neural network. We say that a neural network is deep when it has more than 2 layers. So it's very simple. And you just put basically images, features inside, and at the output you get objects, bounding boxes, and so on. Well, it's not so easy. We'll discuss in the next slide. But for example, you can correct the previous errors. So this is one important thing. The bench will not be here misclassified. He will not be detected as an object. But is this really enough with what we want to do? In the segmentation with deep neural network, we can go further. And we can really segment. Here at a certain distance, it works well. When it's too far, no, but at about 10 to 15 meters, in the case of this video, you can shape the pedestrian. So why it is important? Because well, this is a type of school example, but if with your car you have to avoid objects, you need to know exactly where they are located, and not with a bounding box, you have some mistakes. So, what we can do with deep learning, is it good to use it everywhere? That's a big point. So, we can model any nonlinearity. This is a good point of deep learning. Even if you don't know how to write an equation, you can do it using neural networks. You can generalize. It means usually how you do. You collect data. You split this data in a training data, in test data, and in validation data. And you use the training data just for computing the model. And then you test it against the other data the network never saw. But you will see that he's able anyway to provide very good results. So this is a generalization. The transfer learning is, for example, I worked a lot on modeling pedestrian detection. And I said, oh, now I have to do traffic sign detection. Well, do I have to do everything from the beginning? No. I can use my network already trained for pedestrian, and with a few only iteration, it will work to model the traffic signs. So this is a very important property. Also, you can make all the structure you want. That's a great thing. But on the previous example, the videos I show you, the network takes one picture after the other and decide it's a pedestrian or not. But in the reality, do you really want to do that? Sometimes you need more time to decide. And so recurrent neural networks are for that, to take into account the time. And then you have the other approach that is not directly classifying, is letting him learn by himself. This is what you see as deep Q. So here you just give a set of rules, and you give a chocolate if he do well, and you give a punishment if he does bad. And he will learn the best strategy by himself. This is reinforcement learning. And, well, but what do we need? We need big data. Yeah, that's a problem. We need the labeling of data. That's hard also, because we need to label all the data, even if there's many things to do. You need high computational power. For example, this videos here was, if you compute on a CPU, it will take 2 seconds per image. So you need a GPU. But now, for example, with NVIDIA platform, GPU enable, it's no problem. And it's easy to fool. Just briefly here, the network believes that more than 99% that he got the right answer. But as you see, there's no image, but he detected some object. That's a big problem. So you have to use it with care. So how to test it? That's a big problem. On a plane, for the aeronautics, we say we need 1 billion hours between every fatal crashes of a plane. So can we do that? It means, for example, Google will have 1 million cars driving 1,000 hours. Is it reasonable? Can we really do it? No. And here you have a table that shows some, in California state, you have a lot of regulation, and you have to register and explain what you want to do. So Google drove the most in autonomous and has, for example, 124 disengagement, where the autonomous driving didn't work. And you can see, for example, Tesla had 182. But what is interesting with Tesla, last year when they give information, they said they had 0. How it's possible? So, how to test, how to evaluate random hazard. So there's a lot of simulation to be involved. That's a tough work. And you have to inject faults. For example, simulate braking sensors. Okay. And so you have to test the redundancy. Usually, you know, before we had mechanical or hydraulic steering system. Here it's electromechanical or electro-hydraulic. And you need redundancy motors, for example, for the brake. It cannot happen that you cannot brake when you're in autonomous mode. So redundancy means adding weight to the car and complexity also. So all this is something you should think. And especially you, when you design software, you also need, for example, can I use my deep learning network safely? No, it's very dangerous, in fact, because you cannot predict the error. Can you imagine that you teach him to drive and he gives you the steering, but one day he will make a mistake? What will be the mistake? You don't know. So you need to add redundancy in terms of algorithm also. There's something touch you probably is the cybersecurity. Since you have a link somewhere, a connectivity. First, people want connectivity because they want to use their smartphone in the car. After, you want to simplify the usage of the panel controller or infotainment system by using the voice recognition, but usually it's done in the cloud. So you need also connectivity and so on. So this is very vulnerable. The CAN bus, which is a bus for the car that connects sensor, is very vulnerable, and usually hackers are attacking it. But myself, I do not believe that a hacker will specially hack one particular car. But now you think about connectivity. We are all connected together, as I showed the slides at the beginning. Then it becomes cyber terrorism. And the last point, in fact, nothing will happen without you. Do you want still to drive? Will you accept an autonomous vehicle? So the economy will have to change, because do we want to buy something that we will not drive? So it will be some sharing and this type of stuff. But you can think also of the automated driving as when you are tiring or you are in a traffic jam, it's boring. So sometimes you can drive and sometimes you put in automatic mode, and then it helps also. But as I said before, we will achieve 90% in 2040. So does it mean that we should forget it today, or we can put it on the road? So if we put it on the road, it means we will have accidents. And we are facing dilemmas that you probably heard a lot of. Should we kill people, or should we kill ourselves? Of course, we try to avoid it. But this is not the point here. You have always unpredictable events that may happen. So, for example, the MIT, and here you have a paper published, worked on that, and they built the moral machine. And they got 5 million answers through all the world. It's a website, and with some dilemmas, and people answer who they want to save. And everybody agrees that the best trade-off is to minimize the human damage. But when you say, will you go to this car, and will you purchase it? No, because this car can decide to kill myself. So that's a big problem. And another funny or strange answer, when it was asked what people want to save the most, the answer was cats. If you have a cat crossing the road, people said, we want to save it. And who you want to kill the most? It was a baby. So that's very strange results. And so that's why the question is, can we let the machine... No, I will formulate differently. Should we learn the machine to think as we are thinking? Or should we let her think in her way, find herself or itself the best strategy? Because there's no good answer or good ethical answer in killing someone. Killing is wrong. You cannot find a way to say killing is good. So it's not anymore only an ethical dilemma, it becomes a social dilemma. And I will finish my talk just by saying, when you see a lot of videos, when you see a lot of information, please be critical, because there's a lot of marketing, there's still a lot of work. Of course, it will be cars, and we also are working on, and we expect to deliver about the same time as all other car makers. but it will not work in all conditions. Thus, please consider it very importantly. And to finalize, we opened a special page for this conference, WeAreDevelopers. So if you want to join us and be part of a revolution, you are welcome to apply. Thank you very much.
Sacha, thank you very much. Very exciting talk. Everybody is kind of curious about the speed. One question is, how many kilometers can I go at 350 kilometers an hour?
Yeah.
How many kilometers can I drive at that speed?
For the Concept 1 car? That's a good question. I am at the max speed, I think it's about 50 kilometers.
Okay, thank you. Second question, somebody is asking, where does a driverless car, the computation? Is it in the cloud? Is it in the car? How does it work?
That's a good question. In fact, the computation has to be embedded in the car. Why? Because we cannot lose time sending in the cloud. If there's a link break, well, how you can process or take a decision? So you need a high computation power inside the car. And you have some GPU manufacturers that provide the hardware to do it now.
My final question, I'm a developer. I want to apply with your company. What skills are you looking into? What's special the developers you want to hire?
Okay. So, well, basically, I cannot say we need one skill. We need many skills because we are seeking embedded software development, we are seeking application development software, people who has knowledge in safety critical applications, and so on. But basically, we need talented people that has an open mind and can think differently. That's very important. We don't want to follow, for example, some other companies who doesn't have any strategy. We want different thinking to achieve the goals we set to ourselves. So, if you're interested, please apply. Thank you.
Thank you very much. Give Sacha a big applause.